Hey, all right, 102 students. Here is the second exam. Let's go through the solutions because it would be good for you to kind of self-grade yourself. Not only would that be helpful so that you have a rough idea of how you did, but I don't really have the ability to write on your test and pass it back like I'm used to and like you're used to in a normal face-to-face setting. So I've been doing these solutions, and you can kind of self-grade yourself. And like I said, know A, how you did before I get a chance to grade it, and then B, also this is, you can kind of see where your mistakes are if you have any here. All right, so let's go through this. There's 4 from each chapter, so I'm sure these first 4 are all about energy and power here. This first one says, how much work does a 60-kilogram person do against gravity when walking up a trail that gains 720 meters of elevation? So the definition of work was force times distance. Of course, it's actually the force in the direction of the distance. So the distance is up, so we're talking about the upward force, and that would be your weight. So this would be an mg, and then in place of d, we would put h. In fact, that's how we worked out the gravitational potential energy. So grabbing a calculator, we can have a mass of 60. G is roughly 10, and then times 720 leaves me with the D for the answer, 432,000, and the units would be joules there. All right, another energy one, number 2. A 1 kilogram ball falling freely through a distance of 1 meter loses 10 joules. In fact, that's kind of that same MGH right there. See, there's the 1 kilogram. G would be 10 and a height of 1 meter. So it would lose 10 joules of gravitational potential energy. How much does the kinetic energy of the ball change? And so again, conservation of energy would say that, okay, it lost one type of energy, hence it must gain some other type. So it's definitely going to be a gain, and it's got to be a gain of 10. And so anyway, so B would be the correct answer. So that's a conservation of energy one. A radio control car increases its kinetic energy from 4 to 12 over a distance of 2 meters. Okay, what was the average net force? Okay, so work is the change in kinetic energy. That's the work energy theorem. And work is that force times the distance. Now, to do the change in kinetic energy here, we might have, let's see, a radio control card increases its kinetic energy from 4 to 12. So final minus initial is 8, and the units are joules. So we need a force and a distance of 2 meters would go here, and that has to equal 8. A joule is a Newton times a meter. This is a meter. So force then would be this 8 divided by this 2. So we're looking at 4 newtons. And so that would be A. And probably one more here on energy before we move on to the rotational chapter. If a 60-kilogram sprinter can accelerate from a standing start to a speed of 10 meters per second in 2 seconds, what is the average power generated? So this is a definition of power. This would be energy per time. And in this case, the energy is going to a change in kinetic energy. So that would be a 1/2 mv final squared minus what it started at. But if you go ahead and let me just say, starts from a start, so or starts from rest, accelerate from a standing start, we can just say 0 kinetic energy it started with, and then this is our 2 seconds. So we have a 1/2, what was the mass? 60 we have a speed of 10 squared, and we're dividing that by 2. So let's see, maybe the easiest way to do this is to square the 10 to make 100 and take half of that, so that's a 50. And then also take the 60 divided by a 2, that's a 30. Because then a 5 times a 3 is 15, and then 2 zeros. So this would be our 1,500 watts. And sure enough, the unit would be joules for energy per second, and that's what we call a watt. Although they're all watts, so there's really not much difficulty in knowing that the unit's going to be watts there. All right, so now moving on to rotation. Here we said if the beaters on a mixer make 800 revolutions in 5 minutes, what is their average rotational speed? And so we gave that omega. Of course, depends what units you use, and as I scan the answer, these are all in revolutions. So when I say about how distance did it travel, I'll put it in revolutions, because we could put it in radians or even degrees, but 800 is good. And it could be revolutions per second or per minute per hour, but they're all per minute, so this would just be 5 minutes. So no real unit conversion tough stuff here. Let's see, 5 goes into 8, 1, and there'd be a 3 and 30, so that's 160 revolutions per minute. So it looks like 5 should be C there. A change in the rotational velocity of an object is produced by a net. And then this is the idea of torque. Again, perhaps you remember me saying it many times that the rotational motion is harder than the translational motion, but there's a lot of parallelism, so hopefully you saw those parallelisms. So if you replace things like force with torque, and of course linear velocity with rotational velocity, and of course mass with rotational inertia, but in this case it would be torque. And torque is a little more and a little different than force. So that's why it's hard. So it's not just a word that's different, but that's part of it. But torques go with rotation, whereas force go with translations. So anyways, that would be the correct idea of a torque. A pirate with a mass of 90 kilograms stands on the end of a plank. And so here's a plank, if you will, end of a plank that extends 2 meters out. And so maybe here's the edge of the ship. And we've got the pirate out here at the end. It's 2 meters beyond the gunwale. So there's the gunwale, the side of the ship. It says, what torque is needed to keep him from falling? So there would be a torque rotating it downward, and in order to have no motion, you have to have a net torque of 0. So there's got to be some kind of balancing torque. Perhaps this has bolts in here, or maybe even nails, or maybe it's just simple, a longer plank sticking out the other side and somebody's standing on it. Who knows? But there needs to be enough torque going, what I guess I'd call a counterclockwise direction to balance the clockwise direction. And so just like for translational motion, we know something that doesn't move if its net force is equal to 0. We know something doesn't rotate if its net torque is equal to 0. So besides being kind of a Newton's second law and realizing the net torque has to be 0, we also have to know how to calculate the torque. And so the torque in a clockwise direction is the weight of the pirate and the distance out, which is the 2 meters. So if we take the pirate as a 90 and G as roughly 10 and 2, let's see, 90 times 2 is 180, and then times 10 is another 0. and then the mg would be a Newton, and the distance would be a meter. So looks like we're looking at 800 Newton meters there for 7. 8, and sadly 8 actually has a part C option down on the next page, and I hope you didn't miss that. Although that's not the right answer, so maybe it's just as well if you did miss it. It would narrow your choices to just A and B. But again, about rotation, a solid disk and a hoop have the same mass. And perhaps you saw me in class doing this. I did have a solid disk. It was black, or at least spray painted black, because then we also had a metal piece which we spray painted black so that they looked the same. They had the same radius, and one was made out of a heavy metal and the other one was a lighter wood, so they actually had the same mass. So it fits this exactly. They had the same mass and they said the radius. But the whole point of this question is that rotational inertia, the resistance to rotation, is that it depends not only on the mass, but also where that mass is. And the further out, the more inertia it has. So just like back in 6, where we said, torque and force are not the same thing. It's not just a different word used for rotation. Inertia, or mass, and rotational inertia are not the same thing. And so this one is trying to illustrate that even though they have the same mass and even though they have the same size, it's where that mass is. And so in the case of a hoop, all the mass is way out far, whereas the solid disk, the mass is evenly distributed. So some of it is far, sure, but not all of it. Some of it's close, whereas in the hoop, it's all far. So anyways, the hoop then is going to have a larger amount. And so 8 should be A. Okay, so moving on to number 9 here. 9 would say here, 1 liter of water has a mass of 1,000 grams, or 1 kilogram. And the mass of 1 molecule of water is 18 AMUs. How many molecules of water are there in 1 liter? Now, here's a important point. This 18 is the atomic mass of that periodic table. And if you remember our discussion from chapter 11, actually I should have pointed out, so now that we're done with our mechanics, we're jumping over here to the next 4, which are from chapter 11. But there's 3 meanings to this 18. One meaning, the first one I talked about in class, was the 18 is the number of nucleons. Not really important for this problem. But the other 2 meanings, where you could have the mass of 1 molecule, would be 18 atomic mass units, but the mass of 1 mole would then be 18 grams. Here's why that's important, because if you were then to say that you had this glass of water, or it was 1 liter of water, which is 1,000 grams, and you realize now that 18 grams make 1 mole, you can then say that I have 1,000 divided by 18. This is how many moles I have. So I have 55.56 moles. And so this would kind of be like saying I had 55 dozen donuts. Because to figure out how many donuts I have, I would have to then multiply by how many make a dozen. In this case, they're not a dozen, it's a mole, so I'd have to multiply it by 6.02 times 10 to the 23rd. So times 6.02 times 10 to the 23rd. So this should be about 3.34 times 10 to the 25, which D is the only thing close to that. Okay. What Celsius temperature corresponds to the Fahrenheit scale? And hopefully you kind of caught the idea that if you take the temperature in Celsius, where Celsius measures 0 at ice water, and the Fahrenheit scale is smaller by that 180 from ice water to boiling water, whereas Celsius has 100 of them. This would be the number then of how many Fahrenheit divisions do we have. And so if there's some random temperature in Celsius, say 20, when I multiply it by the 9/5, this would be how much is above ice water. But since ice water on the Fahrenheit scale is measured at 32, these would then be how many divisions are above 32. So plus 32 to get the temperature in Fahrenheit. Now this is also open book, so that maybe this is a little bit easier. And you don't have to memorize that formula. You can just look it up. And so in our case, I'll put in a 77 here and then solve for the temperature on the Celsius. So I guess I'd go 77, and first I'd subtract off the 32. Then I'd multiply it by a 5 and divide it by a 9, and they're looking at 25. So 25 degrees. So answer A. Another one from chapter 11, which of the following doubles with the doubling of the absolute temperature, the absolute temperature of a gas? And so the key to the ideal gas law was to remembering that the temperature is related to motion, sure, but what motion? Momentum, speed, velocity, kinetic energy? What was the connection? Because a lot of times we just kind of say, oh, more temperature, more motion. And that's just kind of a vague word. And I know I started off saying that, but somewhere along the line, I pointed out that let's be more specific to what motion are we talking about. And it's the kinetic energy that it's connected to. So energy and temperature. And of course that's important because these first three all have just V in it, whereas D has V squared. And so there would be a difference when you say you double the temperature, you're actually only increasing the velocity by 41%, because if you take 1.41 V squared, you get 1.41 squared, you get V squared, that's 2V squared. So you only have to increase the speed by 41% in order to double the kinetic energy, meaning you're doubling the temperature. Whereas if temperature was related to either momentum, speed, or velocity, if you doubled the temperature, you would double their speed. And so there's an important distinction between those groupings. Anyways, so hopefully you got that. Temperature is really related, even though we often say the word motion, sometimes we say speed in a kind of a general sense, but the best answer is D by far. And then I think one more from this chapter. Here we have 4 liters of an ideal gas is heated from 300 Kelvin to 600 Kelvin in a container of fixed volume. That's important. If the initial pressure was 1 atmosphere, what is the final pressure? And I know in the lecture I suggested you take the ideal gas law, PV, and you move the NT underneath it because that's equal to R. And so if you call these the initial conditions, which is equal to R, they must also equal to PV over NT for the final. And so we don't have to worry about R. We can just say, hey, these initials equal these final. And then for maybe the simpler of the problems, maybe a couple of these on each side are the same, and so they make it very clear. Fixed volume, 4 liters. So the initial and the final are each of 4, and they would cancel off. So we don't even need to know that they're 4. They would just cancel off. And kind of indirectly, it says here for an ideal gas. So we're talking about the same gas, the same number of molecules. So The number of molecules is the same. Okay. So the relationship here is pressure and temperature. And so this one says, if the initial pressure was 1 liter, what's the final? Now you can see here that the temperature has doubled. So we're really saying go from here from 300 to 600. So if the bottom doubles to be the same ratio, the top has to double. So this would have to go from 1 atmosphere to 2 atmospheres. So I guess 12 would be just B. B as in boy. Okay, well, moving on from that to chapter 13, which has things like, it's still the structure of matter, but now we start getting into, Archimedes' principle and Bernoulli's principle. And here we have 2 cubes have the same size. One is made out of wood and one is made out of aluminum. Both cubes are placed in water-filled aquarium. And here's something real important. The wood block floats. Okay, now remember they're the same size. So if I'm looking at a piece of wood that is floating, maybe something like half of the block is submerged underwater. Whereas the aluminum block, being more dense, would sink. So it would look something like this. So which cube, if either, experiences the greater buoyant force? So this is really Archimedes' principle. We know that the buoyant force is equal to the weight of the displaced fluid. So without really calculating any numbers, we'll save that for the free response, we can hopefully see that the floating object will always displace less volume and therefore displace less weight than the sinking one. So it's this sinking one that's going to have the largest buoyant force. And that might throw you off just because people like to think, well, it's sunk. And it's like, well, it's sunk, you might say, because it's sunk, it doesn't have as much buoyant force. And that's just not the case. It has even more buoyant force than the wood. The reason it sinks, though, is it also has a lot more weight than the wood. And the buoyant force, even though it's more, the buoyant force is still less than the weight of the aluminum, and so it sinks. Where here on the wood, we have a smaller buoyant force, but we also have a smaller weight to it. So it ends up floating. All right, so here a block of plastic has a mass of 50 grams and a volume of 400 cubic centimeters. Will the block sink or float in water? And we had that discussion about density. Density being the mass, 50 grams, divided by volume. And so 40 goes into 50 at one time, and then there's 10 left over. So 10 out of 40 is a quarter. And so it'd be 1.25 grams per cubic centimeter. And so we went through a little argument that a easy way to decide if something's going to sink or float is to look at the density. Anything more dense than the fluid it's in will sink. And so water has a density of 1. So a block of plastic, this piece of plastic will sink. And it's going to sink all the way to the bottom. Let's see, looks like there's another sink. Sink to 80% of the depth of the water. Oh, so like it doesn't go all the way to the bottom. No. See, once it goes underwater, the volume it displaces, and therefore the buoyant force, doesn't change. It's equal to the weight of the displaced fluid. And once it's underwater, it doesn't displace any more water, whether it is 3% underwater or 80% underwater or 100% underwater. So if it's sinking at 3%, it's going to be sinking at 80%. So It just doesn't displace enough water to get enough buoyant force to lift it up. Okay, so that one may pause you to kind of think, but it's not D. It definitely sinks. Okay, here we have a hollow box, has a mass of 200 grams. What is the minimum volume the box could have and still float? So again, and still float. Now, as I read this, I just realize it probably should say float in water. And so we're comparing it to a density of 1 gram per cubic centimeter. So anything more than that would sink, anything less than that would float. So if we're looking at a mass of 200, we would need something at 200 cubic centimeters, because 200 over 200 make 1. Something like that would have a density of exactly 1, and it would just barely float. So it says, what is the minimum volume it can have and still float? So 200, or I suppose you might even argue 200.00000000001, because right at that number, I guess it's neutral in the sense that if you put it underwater, it wouldn't go to the top, it would just stay right there. But if you put it right in the water, it would stay there too, so it would just float, if you will. So, anyways, so they're after C here for number 15. And then I think this 16 should be the last one from chapter 12 before we get into our other thermal stuff in the next chapter. It says a block of metal weighs 9 newtons in air and 7 newtons in water. What is the volume of the block? And I think this is pretty similar to a free response question. I'll have to get to that. But the first thing to realize is this is a lot like the lab. And the fact that there is a difference of 2 newtons is really telling you, I'll call it B, well, I'll just spell it out, for buoyant force. And see, the whole reason if you put it underwater and it reads less when it's underwater is because the water is lifting up and it's reading less by 2. And that's because the water is lifting up by 2. So I think the harder part of this problem is to figure out that this part here is giving you the buoyant force. Because the other part is pretty straightforward. It's the Archimedes Principle. We know the buoyant force is then equal to the weight of the water displaced. So let me just call this mg. And then recognizing that g is roughly 10. And so dividing 2 by 10, I would get 0.2 for the mass. Now I should watch the units. Remember, a newton is a kilogram and a meter per second squared. So this would be 0.2 kilograms. And so this is the m. And anything I think with Archimedes' principle is a little challenging in the sense that it's the mass of what? And in this case, it's the mass of the fluid displaced. So this is not the mass of the object, this metal object. This is the mass of the water that's been displaced. Now, of course, it's been displaced by the volume of the block, and so that's how we're going to do this, because I might write it as 200 grams. And again, knowing the density of water is 1 gram per cubic centimeter, we're really saying this is the equivalent of a volume of 200 cubic centimeters. So it's the 200 cubic centimeters is being displaced. And the reason it's being displaced is because the block is there. So that is the volume of the block. The volume of the block, it's metal, right? So it sinks, right? If it didn't sink, it would be 0 here. This must be then the volume displaced. So 16 would be B. 17, how many calories are required to heat 600 grams of water from 23 to 33? This is just our first and easiest of our thermal equations here, but here's how we calculate the heat when it's changing temperature. We take its mass, which is 600 grams, and then the specific heat, and then this is the water one, so hopefully you memorized it. It's just a simple one. That's the definition of a calorie. It's 1 calorie per gram for each degree Celsius. It warms up. And maybe something a little tricky is to realize we don't put the 23 or the 33. We pick, how much did it warm up? This is the change in the temperature, so it's 10. So 10 times 1 times 600 is 6,000. Grams would cancel, degrees Celsius, and we're looking at 6,000 calories. So 17 should be C. All right, well, continuing on here, 3 more on the multiple choice. It says, which of the following statements does not? These are always harder ones because it says does not correctly describe what happens when a hot block is placed in contact with a cold one. Okay, so heat flows from the hot to the cold. Definitely, right? That the hot one, the molecules are going fast. The cold one, they're going slow. These will bump into these and make these go faster. So the energy goes from here to here. It goes from the hot one to the cold one. Okay. The average kinetic energy of the particles decreases in the hot one. Well, yeah, they're slowing down. They're cooling down. And increases in the cold one. Okay, that's not it. Okay, the temperature of the hot block decreases and the cold one increases. Oh, yeah, all right. So I hope it says D. Temperature flow. Whoa, let's just stop right there. Temperature doesn't flow. Energy flows. And then the temperature is a measurement of its average kinetic energy. So temperature flow makes even no sense from the hot to the cold. Okay, so if you said energy flows from the hot to the cold, which is what A is, heat flows, that would make sense. But that one makes no sense at all. So D would be the one that's not correct. Temperature doesn't flow. All right, if it takes 3,400 calories to raise the temperature of a 500-gram statue by 44 degrees Celsius, what is the specific heat? Well, this is that Q equals MC delta T again, although this time we're not dealing with a water. And we can then put in our 3,400 here. We can put in our mass of 500. We're being asked to find the specific heat. And let's see, is the 44 how much the temperature changed? If it takes this much to raise the temperature by. So that is the change, the 44. We can get the C, the specific heat. So I'll take the 3,400. First I'll divide it by the 500. Then I will divide it by the 44. And so I guess we're looking at 0.1. I'll call it a 5.5. And the units here would be calories per gram per degree Celsius. And so it looks like 19 would be A. On nights, this is a latent heat. On nights when freezing temperatures are expected, why do some fruit growers turn on their sprinkler systems? And it almost sounds counterproductive. Hey, we're going to get it all wet. It's going to be cold. But here's the key, is that if you have liquid water, you know it's above 0 degrees Celsius. And in our area where we have a lot of citrus fruits, the citrus doesn't really damage until about -2 degrees Celsius. So you can actually save your fruits, your citrus fruits. I understand avocados are much lower than that, so you usually don't have troubles with them freezing. And maybe part of it's a lower water content. But the oranges and lemons, when if they get to -2 degrees Celsius, they can be damaged and ruin your crop. So the idea is to spray water on them and keep spraying water on them. Because again, as long as there's a liquid, you know it's above 0 degrees Celsius, which sounds cold, but it's not cold enough to damage the fruit. And in some sense, it actually kind of warms it. I don't mean warm it in the sense that the temperature goes up, but I mean warm it in the sense that it's so cold in the air that as it turns into a solid ice, that has to release the energy. And so this water that's kind of coating the fruit then would be kind of releasing that. And that's how it's keeping the fruit warm. Again, if you want to call 0 degrees Celsius warm. But maybe the air temperature is down to -5 degrees Celsius. And that's what you're trying to do. You're trying to keep the fruit warm at 0 degrees Celsius because the outside temperature is -5 and has the potential, if you don't put something on it to add heat back to it, could easily get below that -2. Anyways, so I guess the best description here would be, as I said, heat is released as the water freezes, keeping the fruit from freezing. And so there's the answers to the multiple choice. All right, let's try, and I guess I'll need some lined paper here to kind of work out the solutions. Maybe I'll start here with number 21 and I'll just read it here. But again, these first two, I'm sure, are back to chapter 7 on energy. And I suggested you do these problems by saying, okay, here is the before and here is the after. Or if you want to go initial and final, that works too, okay? And it says an object is dropped from a height of 80 meters and falls. So, from rest. So if I said before, and I added up the energies, and maybe I'll just put energy equals energy. So energy initial equals energy final. But in this case, the energy initial would all be mgh, and maybe I should put h sub I for initial. I don't have a kinetic energy of 1/2 mv squared here because it says from rest. And so that number would be 0. In fact, maybe to make it a little more clear, maybe I'd put, okay, I got to consider all the energies. It's just the kinetic energy 0, so it's plus 0. So now it falls a little bit, and now it's moving. So it does have, and I'll call it final speed squared, but it's not all the way on the ground, so it has an mgh final. And in fact, if you move this to this side, you get an mg, and then you would have this starting height minus the final height. And so you might call that the delta h. How much did it change by? Now, maybe one of the things that was bothering you is it doesn't say anywhere in this problem what the mass of the object is, and then luckily, I see that it's on both sides of the equation. So when I move this 2 to the other side, I get 2g times the change in height times the square root, or the square root would give me the final speed. So if I grab my calculator here and go 2 times, and I'll take either one. You can go 10 or you can go 9.8. I'll just do a 10 here. But if I go 10 times the change in the height, which is the 30, that's 600. So the square root of 600 is about a 24.9 meters per second for the final speed. And if I go ahead and do a 9.8 and take the square root, and this would be a 24 point, I'll call it 2 meters per second. So I suppose that's a little more accurate, and you do have your calculator, but again, this is grading more on the thinking process. So I'll take either the 10 or the 9.8. All right, another one involving energy here. Looks like this one's the work energy theorem. As I think we said in one of the multiple choice ones, is that the work, which is force times distance, is equal to the change in the kinetic energy. And of course, maybe a little challenging on this one is deciding if it increases or decreases. Because it says here we have a 3 kilogram object is moving left with a speed of 6. So maybe I should put here 1/2 mv final squared minus 1/2 mv initial squared. And right there, that initial, it's already moving 6. But this says right here that there's a force of 40 newtons. And it pushes it in the direction it's moving left. So that makes it go faster. So this would be a positive force in a positive direction. Although usually left we call negative. So if you wanted, we could say this would be a negative force times a negative distance. Maybe that'd be a little more clear. So a negative force and a negative distance. But either case, they're the same direction. So when you multiply them, you're going to get a positive. Whether you take two positives and multiply together or two negatives and multiply them together, you're going to get, let's see, 3 times 4 is 120 with the 0. So it's 12 with a 0, and then that's joules. Okay. So that's how much work you did, force times distance. Okay, so what is the new speed? So this would be a 1/2. Now remember it said the mass was 3, and we're looking for this new speed. Now the original speed was 6. In fact, maybe I'll just calculate this number. That number there would be a 1/2 times a 3 times a 6 squared. So that's a 54. And so if I move that 54 over to here, I have the 120 and then plus the 54. So you notice the minus sign, so I move it over there. Okay. And maybe just to make my math a little easier, this 1/2 times the 3 is 1.5. So if I divide that by 1.5, I would have just then the velocity squared at 116. Now, looking at my units, this is joules, but remember I divided it by a kilogram. So a joule is a kilogram meter squared over a second squared. So when I divide that by this 3 kilograms, that joule would cancel off, and I have meters squared over second squared. So that when I get a final answer by taking the square roots, I take a square root not only of the number and come up with 10.8 meters per second, or not just the number, but I also get the unit here. Okay. So that's the first two on energy. So I can probably fit another one on this page. Maybe I'll call this page 1. Okay. So let's see. This says, if a hard drive on a computer accelerates from rest at a constant rate of 100 revolutions per second squared, how fast will it be turning after 2 seconds? And so this is our standard definition of acceleration. It's just angular acceleration. And so angular acceleration equals the change in angular speed over time. Now for this problem, the angular acceleration is the 100 revolutions per second squared. And then this change in speed would be final minus initial, although the initial would be 0. They made that very clear there when they say starts from rest. And then if we then divide this by the 2 seconds, And maybe if we bring this over, this would become 200, and then we'd have revolution. And a second on each side would cancel. And so the final speed would be the 200 revolutions per second. And maybe I should have circled the answer on all three of those. Okay, so there's the free response, or at least 3 of the 10's free response. I think we have another one here from chapter 8. And this is an angular momentum. That was an important quantity too. Remember, this was that big, long chapter where all the mechanics that we had done from the first 7 chapters was kind of repeated. So there's a lot of questions that could have been asked, and there was no way on a test you could ask everything. But one of them is the angular momentum. And the angular momentum is mass times velocity times the radius. And that's just straight given. The bike and the rider are 80 kilograms, okay. They're moving at 10 meters per second, I guess about 22 miles an hour. And they're making a curve, so they're turning. That's why they have this angular momentum, not just a linear momentum. Although they also have that too, so we could have asked that. But that was really chapter 6. Anyways, it wasn't really for this test. That was for the last test. And then we could just multiply all those together. 8 times 1 times 2 is a 16 and a 0, 0, 0. So it looks like 16,000. It'd be a kilogram. It'd be a meter squared. And be a per second. And there's no fancy name for those. So we don't call it a Newton. We don't call it a joule. We don't call it a watt. We don't call it some of these other ones we're beginning to learn, but that's just the unit. So hopefully you put your units down there too. So, okay. Now leaving mechanics, so it looks like the next 2 should be coming out of chapter 11, starting with the structure of matter. Roughly, about how many atoms are in a small 1 millimeter by 1 millimeter by 1 millimeter cube. Hint, remember, roughly all the atoms are the same size. So if I try to draw a cube here, that what I hope I got a little bit across to you was we could talk about the number of atoms by looking at its mass. And I guess we did that back on one of the multiple choice. We had that 1 liter of water, which turned out to be like 55.56 moles. And basically, we got the number of atoms based upon its mass. But we could also do the number of atoms based upon size. And size was, in some sense, easier, because we don't really need to pay attention to what the material is, because roughly they're all about the same size. They're usually all something times 10 to the negative 10th. The smaller ones have about a 1 times 10 to the negative 10th, and the bigger ones, they get up to 4, I think even 5, some of those F orbital ones. So, I mean, there is a range to them, definitely. But they're all within this, same ballpark. They're like talking about humans. All humans are roughly between 1 and 2 meters. There's a few a little bit over 2 meters. Adult humans there's a few maybe even under 1 meter. But there is no adult humans over 3 meters. I don't think there's any adult humans under a half a meter. So roughly humans, depending on what you're comparing it to, are roughly the same size. So if you stacked a bunch of humans, you can figure out how many humans you needed if you stacked it to the top of Mount Everest. It's so big that, just say, okay, humans are roughly 1.5 meters. Maybe on average they're a hair more than that. But that's the idea of this one. So within what we call order of magnitude. So there is no human 10 meters tall. So you can just say humans are roughly 1 meter, maybe 2 at the most, but they're not 3 and they're definitely not 10. So, but with order of magnitude, same thing. So if you asked how many atoms could you stack in 1 millimeter, you would do something like this. That's a division problem. That's, your 4th grade division is saying how many of these little things can fit into the big thing. So the big thing is 1 millimeter long, and you're asking how many atoms can I fit? Now it's probably real important to make sure you're dealing with the same units, so meters cancel with meters, so we can just get a number, how many. And then if you remember your rules of exponents, you can move that up top, and another rule of exponents is you can just add them, and so that's about 10 to the 7th, which is about 10 million. So you're saying that if I had a little tiny cube that was 1 millimeter high, that's a stack of about 10 million atoms. Now, to get how many atoms are here, I would have to realize that there would be 10 million in its length and 10 million in its depth also. So I would take 10 million and multiply it by 10 million and multiply it by 10 million. And again, adding exponents gives me 7 plus 7 plus 7 is 21. So about 10 to the 21. Not even a mole. Remember, 10 to the 23rd, or 6 times 10 to the 23rd is a mole. So we're about 100th of a mole here. So a lot of atoms, sure, but nothing compared to what it could be, and nothing like the number that was in that glass of water that weighed 1 kilogram. All right, but that's the key, is to connect the size versus mass. All right. So let's move on to 26. So 26 says, here we have an ideal gas. It is heated from 25 degrees Celsius to 175 degrees Celsius in a container of a fixed volume. Yeah, so this is the one I was saying. This is almost really like the multiple choice one. If the initial pressure is 150 kilopascals, what's the final pressure? So I would do this one the same way I was showing you the multiple choice, and the same way I was showing you in the lecture, is go ahead and realize with the ideal gas law, which we often write as PV equals nRT, I realize. But if you just put R by itself and you call, okay, this is the initial, this is the initial, this is the initial, this is the initial, and set it equal to R, and then you make a change, there could be a change in just 2 of these or 3 of these or all 4 of them. So we'll put final, but they got to equal each other. So we don't have to really pay attention to what R is. We just know that those are going to be equal. And for simpler problems, and pretty much this semester we give you the simpler problems. We'll wait until Physics 123 before we give you some harder ones where all 4 of these change. But in this case, it says here in a fixed volume. So volume doesn't change, and they don't give it to us this time. What else doesn't change? And then indirectly, they are saying the number of molecules doesn't change, because it just says this gas is in a container. All right. So then we can go ahead and put in our numbers. It says the initial pressure here is 150 kilopascals. And here is another easily made mistake. This temperature must be on the Kelvin scale. It only works when there's a direct connection between the motion, that's its kinetic energy, and the pressure. So you got to have this on the Kelvin scale. And this one could easily overlook, and you could put in an initial temperature of 25, but this really needs to be, 273 plus 25. So this should be starting at 298 Kelvin. And then on this side of the equation, here's what we're looking for is the final pressure. And again, making the same comment that the final temperature has got to be on the Kelvin scale. So I'm going to add the final temperature in Celsius, the 175, and get 448. So the final pressure here would be something like this. The 150 kilopascals divided by the 298, then multiplied by the 448, coming up with a final pressure of 200, and I think I'll round it to 26 kilopascals. And I guess I should have put Kelvin there, and that would cancel off. Okay. But again, if you put Celsius, you may not even recognize the mistake because it would cancel off. And you go, oh, that's cool, canceled off. But again, this equation that you're using is not even valid except for on the Kelvin scale. So you can't just say, well, the units worked out right. It's not a matter of did the units work out right. And so this would be one of those cases of unit analysis where, you know, our unit analysis back in chapter 1, if you remember, to check those units, because if they don't work out right, you know you did it wrong. But if they do work out right, that doesn't mean you did it right. There could be some other mistake that allowed it to come out that way. And in this case, the mistake would be you're using something that's not even valid, even though the units are valid. So watch that one. Okay, it looks like I can probably fit question 27 on here. Depends how long it is. But let's try 27. A block of copper that measures 3 by 3 by 3 centimeters has a density of, oh, and a little typo, sorry about that. Probably about 3, maybe there were 4 of you emailed me during the test, and I did say you're right, it should be grams per cubic centimeter, not cubic meter. So my bad. Fortunately, I almost sent this out to all you guys. It's not needed for this problem. So the only thing that really that could be used for, as you'll see, is to make sure you know that it sinks. But I think just by saying a block of copper, you know it sinks. So it's got to go completely underwater. Because we know that anything that has a density greater than the density of water would go underwater. Okay. And it would sink to the bottom. And it even says it is lowered carefully into a completely full beaker of water. And so the key here is that you've got this container filled up here, and when you put it in, it's going to displace, and that water is going to flow over. But the real key here is to really, in this question, it says, what is the weight of the water in newtons that spills out of the beaker? And so you need to know, first of all, how much volume flows. And I would say, well, the volume's easy. It's the volume of the cube. And so I guess that'd be my first calculation. What is the volume of water that flows out? And so 3 times 3 times 3 makes 27 cubic centimeters flow out. Which, again, remembering the density of water, would represent 27 grams. Because, again, water, each cubic centimeter is 1 gram. So if, you know, there was a scale over here, when it flows out and you were to weigh it on the scale, you would say it's 27 grams of water. So you can either say it's 27 grams of water or it's a volume of 27 cubic centimeters. Now, the reason I want the mass, though, is it does ask for the weight. And weight is mg. So I need to know the mass. That's the key. And if it's going to be in newtons, mass needs to be in kilograms. So let me write the mass in kilograms and then multiply by the 10 meters per second squared, which makes the 0.27 when you multiply by 10, and that would be newtons. So 0.27 newtons would be the weight of the water that spilled out. So again, you don't need the density of the copper. Okay, good. Let me call that page 2. It looks like we're down to our last 3 here. And so number 28. Here we go. Here's number 28. 28 says that we have a block of metal that weighs 25.1 newtons is submerged into water. Oh, this is a little like the multiple choice one too. It's a hard one, so it's hard twice. But again, maybe the tough part about this is to recognizing there's a buoyant force. And it's that difference. It's the 25.1 newtons minus the 17.2 newtons. Which, I guess if I borrow, I get 11 minus 2, so it's 0.9. And then 24 is 7 makes 7.9 newtons. Okay. Is that right? 24, 25, 1. Yeah, okay. So that's the buoyant force. Of course, now the other part of this is the buoyant force. This is Archimedes' principle. Must equal to the weight of the water that overflows, not the weight of the metal object. We know the weight of the metal object, but the buoyant force is equal to the weight of the overflowing water, or water displaced. This one doesn't overflow like the beaker one, but it does equal to the weight of the water displaced. Okay, so using the idea from the last problem that's roughly a 10. If I divide by 10, I get 0.79. That would then make units in kilograms, which would then be 790 grams for the mass. And then, of course, finally, that's the water displaced. Remember that every gram of water is also 1 cubic centimeter. So this would be 790 cubic centimeters for the volume that's displaced. And it's being displaced because that's the volume of the block. So that must be the volume of the block. And then finally, chapter 13, and looks like we've got 2 from 13 here. 29 says that we have 27 grams of aluminum, and then it gives us the specific heat of aluminum at 100 degrees. This sounds a little bit like the lab we did, where the metal piece was in the boiling water, and then we moved it over into about the same amount of water, about 33 grams, and it came out of the sink at about 19 degrees Celsius. What is the final temperature, assuming no heat is lost or added to the outside? So I would say then the Q coming out of the hot one is equal to the Q going into the cold one. Now I should be careful in terms of absolute value. Because if I put MC delta T, and the other one is MC delta T, this first one being the hot object, so this right here is the aluminum, and this right here then would be the water. So here's my H2O. I need to be a little careful because one of these is going to be cooling down, and its change in temperature is negative. That would, I guess, be the aluminum one. And the way I was thinking of it is energy lost is equal to energy gained in terms of absolute value. I'm not trying to say a negative is equal to a positive. I'm trying to say the absolute value. One loses it, so that's negative. The other one gains it, that's positive. But the magnitude of them is the same. So I do need to be careful with this aluminum one. Okay. And in fact, now I can put in my numbers. This is 97 grams. The specific heat of the aluminum here is given as 0.22 calories per gram for each degree Celsius. And here I want the absolute value. I mean, normally we would put final minus the initial of 100. But that would give us a negative number. And so let me write it as 100 minus the final temperature. So that this number, this loss of energy, is not a negative number. Because, again, my thinking at the beginning is in terms of absolute values. So if I just blindly do MC delta T, I'd get a negative here and foul up my math. Okay, so energy lost, but the absolute value of the energy lost. So the negative is converted into a positive, equals the energy gained. So the mass of the water was the 33 grams. The specific heat of water is 1 calorie per gram per each degree. And the change in temperature, and we don't have to do anything fancy here, is final minus initial, the initial being 19. And since the water's warming up, the absolute value, this is already a positive, right? This is the one that energy goes into. So the change in temperature is a positive. This is already a positive. So again, the only one we've got to be careful with and then switch the order to make sure we get a positive number is right here, the aluminum one. Okay, so maybe now we can simplify this. There's a lot of ways of simplifying it. But I think I'll just take the 97 and multiply it by the 0.22 first. And before I even do a distributive one, I'll then bring over the 33. And I don't even need to do a calculator for that, but also bring over the 1. And so this comes out to be 0.647 times 100 minus final temperature equals final temperature minus 19. So when I take the 0.647 and multiply by 100, that's 64.7. And then 0.647 times final temperature minus 19. And then you can kind of see that if I put the final temperature together, this would be a 1, and when you bring it over, it becomes plus 647 final temperature. And then this 64.7, adding 19 to it, makes an 83.7. And so a final temperature, 83.7 divided by 1.647. And we're looking at about a 50.8 degrees Celsius for the final temperature. Which always is a number that surprises me because the water, a lot less water, only goes up 30, even though the metal cooled down at about 50. So the metal cooled down a lot more. But again, this was one of our discussion questions in the lab, and the reason for that is the specific heat. It just takes a lot of energy to either warm up water. And you're seeing that. Even though there's so much less water. See, there's only about a third as much water. It's still overall warmed up less than the metal. Just this number is so big. Hard to warm up water. Or maybe hard's not the correct word. Maybe the word I should use there is it takes a lot of energy to do it. Which often means hard. Okay, so the last one here, and maybe so I can read it a little better and have some room to work, is right here, number 30. How much heat does it take to bring 25 grams of ice from negative 15 degrees Celsius to fully boiling away? That is, it's 100 degrees Celsius and it's steam. So the total energy really has to be added up in a couple of ways, because we first have to warm the ice, we then have to melt the ice, which now we have water. We have to warm the water until it comes to a boil, then we have to boil it all away. So there is 4 pieces of this. The first one is an MC delta T. That's a warming of the ice. The next one is the melting of the ice. That is the latent heat, and that would be a fusion. There is again an MC delta T, because now we're in the liquid phase and we're warming it up. And we wouldn't want to combine those two together. They are the same masses, but they don't have the same specific heat, and we're not warming them up by the same change in temperature. So we got to have a separate calculation for warming up which is now water. And then, of course, once we get it to a boil, then it takes an energy to vaporize it. So this first one would be the mass, which is 25 grams. And if you look up the specific heat of ice, you'll see it is about 1/2 calorie per gram per each degree. And the ice you would warm up just 15 degrees. I'll maybe just even do that calculation. So 25 grams times 1/2 times 15. So this is 187.5 calories to warm up the ice. But now here, the 25 grams and the latent heat of fusion is 80 calories per gram. And I'll do that one now too. So that would be the 25 times the 80. And so that's 2,000. So it takes a lot of energy to melt it. So really warming up ice is really hardly anything. It's the melting of the ice that's going to take a lot of energy. Well, that's why if you ever had ice in a freezer, you pull it out. A lot of freezers are set around negative 15, negative 20. And you throw that into the water. It quickly warms up to 0 degrees and starts to melt. But then it stays at 0 degrees, continually melting and then bringing the water down, and you have nice ice water at 0 degrees. But this first part of it, just warming up the ice is to the melting point, is such a small amount. Well, let's keep going, because once we then melt it, we got to bring it up to a boil. So that would take the 25 grams. And now we're at water, and water has a specific heat of 1 calorie per gram per each degree. And we are going to warm it a full 100 degrees to get it to a boil. It's 100 degrees Celsius. So from 0 degrees Celsius to 100 degrees Celsius. So that would be 2,500 calories. And that's quite a bit of energy too. And I find it interesting that the amount of energy to bring it to a boil, which seems like a lot, is the same just to melt it. So that tells you kind of how much it is to melt. Although that is a little smaller than that one, but not by much. And in fact, if you've ever boiled water away, this is the big one right here. And maybe I'll put it on the side of my paper here. But the 25 grams, and it takes 540 calories to boil 1 gram. So the most energy by far is 25 times 540. And so this is 13,500 calories. Way more than all of these, even combined, which makes sense. That's why, you know, if you ever have tried to boil water and completely boil it away, maybe in a lab, usually cooking, you don't try to boil it away. You get it to boil and then you start to cook it. In fact, maybe for cooking, it's probably good that it doesn't boil away. It takes a long time. But if you did leave it on there, it takes a really, really long time. It's a really, really lot of energy before you boil it all the way. But now we've got to add all these together. So coming up here and grabbing the 187.5 and then the 2000. And then looks like I didn't put this in my calculator, so let me put 2,500 and then copy and paste the 13,500. I add all of that together, and it is 18,187. Actually, those were pretty easy in my head. 0.5 calories. And so there's the last one. Hope you did well. All right, take care.